Hello everyone, Mr. Minnick's my name, math is my game. This morning it's a special day because it's a Monday, Wednesday kind of day. Today we're talking about something that apparently we need to talk about because some people have a lot of misconceptions about this P word, probability. So let's look at the very first problem that I gotcha with. Example 1, probability of heads. Well, before we can answer that question, and I'm assuming we're talking about a fair coin being flipped, we really need to know the definition of probability. In a stats class, probability is defined as this: F divided by N. So you're probably thinking to yourself, what is F? F is the frequency. F is the frequency of desired outcomes. What's an outcome? An outcome is something that happens in a trial. What's a trial? Something that's happening. Some kind of event, like a coin being flipped. So the N, you might ask yourself, what on earth is N? And notice I used capital N. N is the number of outcomes possible. So probability is a fraction. It's a ratio. That's why it's in Chapter 8 in some Algebra 2 textbooks. That's why it's going to be on this chapter test. So if we talk about this, there's one thing that's nice to know. And this will be one of the other ones too. Anybody ever hear of that word? We're not talking about the final frontier, which reminds me of Dr. Spock. You all know he had 3 ears, right? The right ear, the left ear, and the final front ear. Sample space is a list of all possible outcomes of some event, of an event. So there's several different ways to compute probability. If you happen to know what the sample space of an event is, it makes finding the probability of that event so much easier. It's almost foolproof. You would have to be a complete, I don't want to use an offensive word here, but you'd have to be a complete idiot to not be able to calculate probability if you saw the sample space and you truly understand what events we're talking about. So let's think about flipping this fair coin then. The sample space of flipping a fair coin, we call sample space S. It's the set. It's the set of all possible outcomes. So we use the braces. So what can happen when you flip a fair coin? You can get heads. And I hope this next one doesn't offend anybody. I'm sorry in advance when it does. Heads and tails. Okay? So let's think about this probability of heads then. The probability is the frequency of desired outcomes. Well, we're talking about heads. In our sample space, how many of those events, what's the frequency of the desired outcome? Bueller. Well, we're just talking about the numerator right now. The frequency of desired outcomes. 1, there's one head. And what's the total number of possible outcomes? 2. So the probability of heads is 1 divided by 2. I don't want to offend anybody today, but those of you that said 50-50, that's not the probability of getting heads on a fair coin flip. It's not 50-50. And just about everybody thinks it is. That's why I started with that one in the Kahoot. A lot of people miss that. I remember when I taught freshmen, I would get 99.9 out of 100 freshmen on that one. It's not because you're idiots, it's just because you didn't know what the definition of probability was. Nobody's an idiot. Well, some people are, but that's debatable, and I'm not going to go there today. So anyway, let's take a look at probability. Here's some things about probability. Probability. So again, it's defined as the number of desired outcomes. The number of desired outcomes. I forgot the C. The number of desired outcomes over the number of possible. outcomes. So the nice thing about the sample space method is however many things are in our sample space, that's going to be our denominator anytime we calculate a probability problem. So if we can find the sample space, finding probabilities, a piece of cake or a piece of pie. So we did miss Pie Day. That was kind of a bummer. We're going to have a food day once before the year's out, maybe twice. So probability of event A, that's red. That's red. Probability. It's red. Probability. The probability. Probability of event A. P of A. It's kind of like function notation, but it's not a function. It's just read as the probability of event A. There's a lot of properties about probability. You might know some of them. There's a specific interval in which probabilities lie. Anybody know what the interval is? From 0 to 1. Nice. And anytime an event has a probability of 0, there's a special name for that event. Tom Cruise happens to know it 3 times. It's impossible. Good. Impossible. Impossible. And if the probability of something is 1, we say it's sure to happen. There's another word, a C word that ends in N, that we use. A C word that ends in N. What is it? Not common. Certain. A certain. Anytime the probability of an event is 1, we say it's certain. It's certain. So one final point about probabilities. Probabilities can be written as percents. They can be written as fracciones. They can be written as decimals. It's very uncommon to see probabilities written as a ratio. Possible, but not likely. So usually we see probabilities written as a percent, as a fraction, or as a decimal. How's everybody feeling? So you're probably wondering, well, what in the world's that one about the 4 coins being flipped? So let's look at that one. Example 2. Probability of 2 heads on 4 coins. A lot of people miss this one, not because they're idiots, because they don't understand sample space and because they don't know sample space. If we were to flip 4 fair coins, we could get heads on every single one of them. Everybody with me on that? We could get tails. Now, keep in mind, these are 4 different coins. So maybe we get tails on the first one and heads on the other 3. Or maybe we get heads and then tails and then heads and then heads. Or maybe we get heads, and then tails and then heads. Or maybe we get heads and then heads and then heads and then tails. Also, we could get tails, heads, heads. We could get tails, this is tough, heads, tails, heads. We could get tails, heads, tails. We could get heads, tails, heads. We could get heads, tails. Are you serious? I had HH, oh, so that's supposed to be HHTT. HHTT, sorry, thank you, good looking out. HHTT, HT, and then what's the last one? HHTT, I already got that. HTTH, good looking out. So, okay. And then, so that's when I have that, so then I could also have, let's see, I could have heads, I already got heads 3 times. I could have tails 3 times. So I could have tails, heads. I could have tails, heads, tails. I could have tails, heads, tails, and I could have heads, tails, and I could have all tails. And you're thinking to yourself, that's a waste of time. No, it's not. That's the way to get the answer to a probability question. Definitively, beyond the shadow of a doubt, with great certainty. How many events possible are there? Or how many outcomes are there, I should say? How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? If you know the sample space, you know your denominator. Probability is the number of favorable outcomes divided by the total number of outcomes. What's our favorable outcome? Heads twice, right? How many of those are there? These 6, right? These 6. So the likelihood of 2 coins showing heads out of 4 being flipped at once is 6 out of 16. Now you guys know how to reduce fractions. So that's going to be 3/8. And I hope that at least one person in here would know the decimal equivalent of that. If you wanted to write that as a percent, 37.5%. Okay? So sample space is a big deal. It's a very big deal. Okay? If you understand sample space and you have the time and the resources to look at the sample space, there's no excuse to miss a probability question, ever. If you're too lazy or you don't want to think about it, well, chances are you might miss it. You might miss it. So far, so good. Any questions? There's got to be a question. No questions? All right. So let's look at odds then. Let's look at odds. Odds are defined as the number of desired outcomes, divided by the number of undesired outcomes. So if we think about comparing probability to odds, if we're talking about the same event, the numerators are going to be identical. The denominators are going to be different, though. Some bullet points about odds is they are almost always written as a ratio. We almost always write these as a ratio. So a specific instance, if it's 3-to-1, we would write 3 and then the preposition 2-1. Or maybe we would write 3 with the colon 1. It's not real common to see odds written as a fraction. Sometimes they are, but it's not common. Usually odds are written as a ratio. So one thing that they like to do on the ACT is to tell you this. They tell you that the probability of event A, so here's example 3. The probability of event A is equal to 7 divided by 13. Find the odds against A. So here we started getting into some language that's kind of unusual. So let's think about this event A. Let's look at the sample space of A. And let's think about what this looks like. We have no idea what's going on in here, but we do know there's how many events in this event A. There's not 7, there's 13. And we know how many of them are favorable. 7 of them are favorable. So we could say, well, 1, 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5, 6. 7 are favorable. 1, 2, 3, 4, 5, 6 are unfavorable. You with me so far? Okay. So we're asked to find the odds against A. So these green things are for A, right? And these red things are against A. So if we're finding the odds against A, then the odds against A, what would that look like? It's going to be the desired outcomes. What are the desired outcomes? These ones. Does that make sense? Oh gosh, I'm tripping here. These ones are the desired outcomes if we're talking about the odds against A, right? So what's it going to be then? 6 divided by the number of undesired outcomes. Well, how many undesired outcomes are there? 7. So it'd be 6 to 7 or 6:7. What do you think about that? Does it make a little bit of sense? Un poquito. We have several more terms to get down. Several more terms to talk about. So language is kind of weird. Odds in favor of, odds against. Okay. So events. Oh man, when we start talking about events, there's independent events. Independent Events. Love independent events. They're events where the outcome of one does not affect the outcome of the other. The outcome of one does not affect the outcome of the other. So this is assuming we're talking about two independent events. Okay, if you're talking about three, none of them will affect any of the other ones as outcomes. So let's think about this. We're in Garrettsville. A tornado siren blowing in Garrettsville. And someone buying a taco in Columbia. If a tornado siren sounds in Garrettsville, does that have any outcome on whether or not somebody in Columbia buys a taco? It does? There's always that extreme, far-fetched argument you could make. Well, maybe they have supersonic hearing. No, they don't. Okay. The winds generate enough winds to... Yeah, there's always a far-fetched argument, but hopefully you get the idea, right? So let's think about this. The type of example that you're going to see is something like draw a card from a standard deck and flip a coin. Flip a fair coin. If you draw the ace of spades, that has no outcome whether or not that coin's going to be heads or tails. Those are said to be independent events. Everybody with me so far? So what we start to talk about then is probabilities of two events happening. So let's think about this. What's the probability of getting an ace, of getting an ace and heads? So if we were to consider these things separately, that might be kind of cool at first. I don't think many people understand what a standard deck of cards looks like. Some people do. When you think about cards, of course, there's 52. There's hearts, there's diamonds, there's spades. I can never draw that one. It kind of looks like a shovel and kind of, well, anyway. Okay. So there's four suits, and in each suit there's a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, Jack, King, Queen. So these cards down here are called face cards, right? These three. Oh my gosh. How can I forget the ace? Is the ace considered a face card? I don't know if ace is considered a face card or not. Okay. But anyway, so how many cards are there in each deck then? There's 13, so 52. Everybody with me so far? Okay. So it could be either or. Thank you. Good looking out. Appreciate the info. So let's look at just the probability of getting an ace for a second. The probability of getting an ace then, the probability of getting an ace would be 1 out of what? 4 divided by 52. Or if you wanted to reduce that down, those are both even. We could divide by 2 because your 6th grade teacher said divide them by 2. So that's 2 out of, hey, those are even again. 2 out of 26 or 1 out of 13. Everybody good so far? Okay. And we know now, we know that the probability of getting heads on a fair coin flip is how much? 1 divided by 2, right? So let's think about this. We're talking about the one event happening and the other event happening. It's kind of unlikely that we'd get an ace, and it's about it is exactly a 50% chance of getting heads. So the probability of getting ace and heads, do you think that's more or less likely than either one? Less. One thing that I want you to understand is when you have independent events and you find the probability of the one and the other, it's very unlikely. It's kind of like finding a unicorn. It's not impossible, Unicorns exist. I believe in them. I've seen them. I've seen them in Walnut Creek, Ohio, just there this weekend. Beautiful town. Yeah. So whenever you find the probability of two independent events, note to self, the probability of two independent events, the one event and the other, you multiply their probabilities. You multiply their individual probabilities. So this would be 1/13 multiplied by 1/2, or 1/26. Okay, so anytime you have independent events and you're finding the probability of the one and the other, you multiply their probabilities. Okay, so to be clear, for independent events A and B, the probability of A and B is the probability of A multiplied by the probability of B. Got him? So now we get to talk about playing the harmonica and eating Taco Bell. Could you imagine playing the harmonica and eating Taco Bell? So, so there's another type of event. There's another type of event called mutually exclusive events. Now, a lot of times we get so hung up on time. Don't get hung up on time. They're events. They are events that cannot. There are events that cannot occur concurrently. And again, you could make an argument that they could, but oftentimes they can't, like playing the harmonica and eating Taco Bell. That'd be a mess. Your harmonica would be ruined. I give a shout out to Ethan Milko. He gave me that example a few years ago. It was the funniest thing ever. Those of you who are going to take applied math next year, you're going to need to come up with two mutually exclusive events. Can you think of some events that can't happen at the same time? Rubbing your stomach and patting your head, keeping your eyes open and sneezing. Okay. So here's one last example today. One last example, and then we'll do our other Kahoot. Here we go. Example. Find the probability of getting a red card or an ace. Let's find the probability of getting a red card or an ace. Well, let's think about our deck of cards. There's 13 red ones. There's 13 red ones. There's 13 black ones, and there's 13 black ones. And there's an ace here, and there's an ace here. And there's an ace here and an ace here. Now let's think about this. We said if it's a probability of one thing and the other, we multiplied. Because it's less likely to have both of them happen. But if it's the one or the other, it's more likely to have that happen, right? Because we could have the one happen, we could have the other happen. So you know what we do when we find these probabilities? We don't divide them. We add them. We add them. So let's think about the probability of a red card for a second. What's the probability of a red card? The probability of a red card is 1/2. And the probability of getting an ace, we already saw that. What was that? That was 1/13, right? Maybe it's going to be more handy to talk about a red card's probability being 26 out of 52 or 13 out of 26, right? Okay. So the probability of getting a red card or an ace then would be the probability of getting a red, which is 13 out of 26, plus the probability of getting an ace. What's the probability of an ace? 1/13. So let's think about this. We think that this is going to be, oh gosh. Um, Maybe I need to make this, can I make this 226? Is that okay? Is that all right? Okay. So that's 226. So that's 226. So that's 1526, huh? Let's think about something. Red or an ace. Red or an ace. So there's 13 red ones. There's a total of, oh no, there's 26 red ones, and there's 4 aces total, right? Something's not right. I think there's something that's off. Because that would be 30. That'd be 30, right? Let's think about that. 30. There's 26 and 4, but aren't there some that double up? Aren't there some that are red and an ace? And aren't we kind of counting those twice? So don't we have to subtract that out? We can't count those twice. So we have to subtract out the ones that are a red and an ace. So how many are reds and aces? 2 of them. 2 out of the 52, right? Is that 2 out of the 52 are red and aces? Okay, so that's minus 126. So that should be 14/26 or 7/13. What do you think of that? A little confusing. Anyway, the point of the story is if it's a probability of 2 mutually exclusive events, it's just the sum of their probabilities. If they're mutually exclusive, if they're not mutually exclusive, like red and aces are, then you have to subtract out the probability of the one and the other. Okay. So, anyway, the probability of A or B equals the probability of A plus the probability of B for A and B mutually exclusive. Okay. If A and B are mutually exclusive, it's just the sum of their probabilities. If they're not, then you got to subtract out the other one. So that's it. I know it's been kind of crazy, kind of impromptu, a lot of information in a half an hour. But I hope that you now know the difference between probability and odds. Do you? All right. So that's it. It's been real. It's been fun. Shout out to my first period class. Shout out to my second period class. Good luck on the next Kahoot.